This video analyzes the various parameters that affect the height of a binary search tree and ways to overcome the same. Consider you are given a list of n unique numbers, maybe the identification numbers of books in a library or anything of that sort. There are Q queries that need to be answered. Each query either asks you to insert a new element into the list or asks you to check if an element already exists in the list. It is assured that the list will never have duplicate entries. For each query of type 2, print yes or no as the answer. One of the approaches would be to store all elements in an array and insert new elements to the end of the list, taking constant time. To check if an element already exists, all the elements of the array need to be compared against, taking linear time. So, the overall time complexity happens to be big O of n times q. Another approach would be to sort the list in ascending or descending order and maintaining this order invariant throughout. To insert a new element, it would take n steps as all the elements greater than the new element needs to be shifted right. Binary search can be used to check if an element exists. But the overall time taken still remains the same. The insertion took longer in the second approach unlike the first one. A way to insert a new element in between without having to shift all elements to the right would have reduced the time taken. Similarly, the second approach used binary search, reducing the time taken to search, by a large factor. We can use binary search trees to get the best of both worlds. Insertion and search can both be done in time proportional to the height, which is usually small when compared to the number of nodes. But there are a few cases where they still don't work well. The height of a binary search tree can be as large as n. The chain structures make insertion, deletion, and search equivalent to that in arrays. A binary search tree with n nodes can have a height anywhere between log n to the base 2 to n. We have seen that a binary tree with a certain height can have at most 2 to the power of height, -1, nodes and at least height number of nodes, which explain the minimum and maximum height criteria. A binary search tree functions the same as long as the properties are retained. It has no specific ordering that needs to be followed. That is, any node can be the root and any node can be placed anywhere as long as in-order traversal gives a sorted list. The two trees shown are equivalent binary search trees but have different heights. Hence, the tree below is preferred. A few constraints can be imposed to reduce the height of a binary search tree. Such constraints need to work without taking a high amount of extra time to avoid spending more time on balancing rather than doing required work. Some of the constraints try to minimize the difference between heights and/or sizes of left and right subtrees at each node of the tree. Any binary search tree can be balanced in big O of n using an array. In-order traversal is used to get the elements in sorted order. At each point, try to split the array into two, equally, and recursively create binary search trees in both arrays. Use the middle element as root and set the left and right subtrees that are obtained by the recursive call. Consider the sorted array as shown. We first consider the middle element and create a node representing it. Then recursively generate the left and right subtrees as shown. When there are frequent insertions and deletions, the balanced nature of binary search tree might be lost. Using array each time will not be feasible. Self-balancing binary search trees induce a few constraints so that the nodes are modified accordingly as the various operations are done. AVL trees ensure that the difference in height of left and right subtrees of any node is never more than 1. AVL trees and red-black trees both perform very well by doing some extra work during insertion and deletion to avoid a lot more work that needs to be done later. Splay trees are another kind of trees which move the frequently used elements closer to the root and reduce the total time taken. Binary search trees can be combined with heaps, which are complete binary trees to give rise to a new data structure called treep. They support a huge variety of operations and are hence useful when different features are necessary within the same context. But treeps usually perform tasks by chaining together a series of smaller tasks and hence have a larger constant multiplier associated with the operations, when compared to other data structures that do the same task. That is, a treep might take longer than a binary search tree in similar situations, but Treep reduces the chances of having to deal with the worst cases. For example, chaining can never happen in Treeps if priorities are properly initialized. We'll go into more detail about the trees mentioned in the upcoming videos. We'll also introduce you to various other mind-blowing data structures. Till then, stay tuned. Happy coding!